Hi everyone, it's me, Dr. Wolf, trying to explain section 6.3 to you. Hope you're having a great break so far, and this video is to explain pages 19 to 29, which is section 6.3 of your chapter 6 note packet. So here we go. Read along with me and I'll explain the details more than what's printed here. So I'm at the top here. Section on binomial and geometric random variables. First, we let this random variable x represent a count of the number of occurrences of some outcome of interest in a fixed number of trials. We've seen that that type of variable is a discrete variable, and we're about to talk about a special scenario where a probability distribution of x is called binomial if it has each of the following four conditions. First, when we do some random outcome here, we're talking about a fixed number of trials of a chance process. Second, the end trials must be independent. Third, the outcome of each trial must be able to be classified into only one of two categories, which we're going to label as success and failure. And then finally, the probability of success, P, must be the same for every trial. So if we have these four conditions, then that special counted variable x is a binomial distribution with the parameters n and p, n representing the number of observations or the number of trials, and p the probability of success. Special note. Most often when we take a simple random sample of size n from a population, we do so without replacement. This is going to change the probability of observing a success on every trial. However, as long as the size of the population, which we'll call uppercase n, is at least 10 times the size of the sample, lowercase n, then the random variable x still has an approximate binomial distribution. We'll ignore the fact that we've technically destroyed the independence condition, as well as the same probability of success on every trial. So we call this, in the future, we're going to call this the 10% condition. And the idea is the size of the sample can be no larger than 10% of the population. And then another memory tool for that list of four items is this little acronym BINS, B-I-N-S. B for by, two outcomes. I for independence. N for fixed number of trials, and S for same probability of success. So now if we look at an example on the bottom of the page, our job is to decide whether the random variable is binomial or not. So in this exercise, we are going to put names of students in your class in a hat. We're going to mix them up and draw four names without looking, and let the variable y be the number whose last names have more than 6 letters. Well, again, our job in deciding whether or not something's binomial is to think about B-I-N-S. Do we have two outcomes? Yes, the name either has more than 6 letters or it doesn't. I, independent. Unfortunately, that one's going to fail because we're sampling without replacement, pulling names out of a hat. N, fixed number of trials. Well, yes, we're going to draw 4 names. And then S for same probability of success? Nope, that one fails too. So the random variable y here is not considered binomial. Okay, I've turned to page 20. Next example. Exactly 10% of students in a school are left-handed. Select 15 students at random from the school and let W equal the number who are left-handed. Well, now I've written out in order the 4 conditions. First, clearly a fixed number of trials. Independent as long as the size of the school is at least 150. Remember, we have this 10% condition, so that seems reasonable. Third, 2 outcomes, persons either left-handed or not left-handed, success and failure. And then finally, number 4, the success probability P equals 0.10 is the same for every trial. So we have B for binomial, I for independent, N for fixed number of trials, and S for same probability of success. Example 74. One of these is binomial and the other is not, and let's see if we can figure out which is which and why. First, A. When an opinion poll calls residential phone numbers at random, only 20% of calls reach a person. You watch the random digit dialing machine make 15 calls. Let X be the number that reach a person. And B, when an opinion poll calls phone numbers at random, only 20% of calls reach a live person. You watch the random digit dialing machine make calls. Y is the number of calls until the first live person answers. Well, in part A, we have all four conditions. There's definitely a fixed number of trials, independent, same probability of success with two outcomes either reaching a live person or not. But in part B, we see that we're not counting successes and failures. We are going to count just the number of calls until we get a live responder. So that's going to fail. We fail the fixed number of trials scenario. And this part B is foreshadowing what's to come. This type of random variable y in part B is going to be called a geometric random variable, because we are often interested in a variable that counts how many times we have to do a chance process until the first success occurs. Those will be geometric random variables. Okay, I've flipped to page 21. Well, now that we know how to identify a discrete variable x as binomial, we'd like to show you some methods for calculating binomial probabilities. So first example, back to flipping coins. Let's flip 4 times and let x be the number of heads observed. Part A, let's talk about the probability distribution of x. Part B, let's draw its histogram, and then in C, let's calculate a mean and standard deviation. So first, if I'm going to create a probability distribution based on the methods of chapter 5 and 6, you can see here that we can list out all possible outcomes for flipping a coin 4 times, meaning we listed out sequences of heads and tails. If we define x to be the number of heads, then you can see I've filled out the x values for each outcome in the sample space. And now for each of these probabilities, because there are 16 equally likely outcomes, we have a 1/16th chance of observing any one of those sequences of heads and tails. Or, by the independence multiplication rule for independence, if I want the probability of h, it's a half times a half times a half times a half, which is 1/16. So now we see that x, the number of heads, could be either 0, 1, 2, 3, or 4. For x equals 0, it would be on this outcome, 1/16. For x equals 1, we see that happened 4 separate times, so 4/16. For x equaling 2, we see that happened 6 times in the sample space, so 6/16, 4/16 for 3, and 1/16 for x equaling 4. And then this table is called the probability distribution of x, and this is its probability histogram. In part C, if I want to get the mean and standard deviation of x, well, again, the methods of section 6.1 have told us that we can create 2 lists in our calculator. List 1 for the values of x, list 2 for the corresponding probabilities. Running that one varstats command could give us mu x equals 2 and sigma x equals 1. Well, now some probability calculations in D and E. If I want the probability that x equals 3, you can see that I've already created that up in the table, and I can just write 4/16 or 0.25. And if I want the probability in part E of getting at least 2 heads, look at my notation again, at least 2 is 2 or more. So the probability then that x equals 2 or 3 or 4 for this chance process, go to that probability distribution and simply sum those probabilities. 6 plus 4 plus 1 makes 11/16. Okay, I flipped to page 22. So now in that example with the coin flipping, you saw us use many laws of probability from chapter 5 and some of those random variable concepts in section 6.1. Well, if this coin was flipped 5, 6, or even 20 times, we would have a very hard time answering these questions with only the basic laws of probability. But by recognizing the coin flip as binomial, where there's a fixed number, n, of independent identical trials with 2 outcomes and the same probability of success, now we can call that random variable x, the number of heads, a binomial variable where n is 4 and p is 0.5. And now I'm going to show you some formulas for calculating probabilities with binomial random variables. So first we have this so-called binomial probability distribution formula. If x is binomial with those parameters n and p, then the probability that x equals k, meaning the probability of finding exactly a certain number of k successes, we can do the following formula. We can do a combinatorics binomial coefficient, n choose k, the success probability p to the k power, and the failure probability 1 minus p to the n minus k power, where k, the number of successes, is anywhere from 0 to n. So again, n is number of trials, p is probability of success, and this nk binomial coefficient is expands out in factorial form to n factorial divided by k factorial times the quantity n minus k factorial. Well, in case it's been a long time since you've seen factorials, a factorial is a mathematical shorthand symbol for a product of integers from the number down to 1. So 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. Factorial symbols can be found in your graphing calculator. Put that number 5 on your home screen, press the math key, arrow over to the PRB key. At option 4, you'll see the factorial symbol. Press enter, and your home screen will then tell you that 5 factorial equals 120. You can get that to show up on your calculator screen. Well, next, this binomial coefficient, nk, well, that's the same as some of you may have seen, especially if you're studying for the SAT. That's the same as this symbol nck, where this uppercase C stands for combinations. A combination is an arrangement where order doesn't matter, where there'd be k successes and n minus k failures. So basically, we're talking about those arrangements of heads and tails, where k of them are heads and n minus k of them are failures. So if I wanted to, for example, figure out the value of the binomial coefficient 4, 3, that means in the 4 trials, how many arrangements are there of 3 heads and 1 tail? So if we use this combinatorics formula, 4, 3 expands out to 4 factorial divided by 3 factorial times the quantity 4 minus 3 factorial. So if I show you that work, it's 4 times 3 times 2 times 1 over 3 times 2 times 1 multiplied by 1. Factorial, which of course is still 1. The 3, 2, 1 and the 3, 2, 1 cancel. This leaves me 4. So notice what I've calculated. There are 4 arrangements of the scenario, 3 heads with 1 tail. So 3 heads with 1 tail. Check out why there's 4 separate arrangements, and this is what the binomial coefficient calculates for you. That tail could be in any one of the 4 spots right here for the coin flipping. Okay, so you see that there are exactly 4 arrangements of 3 heads with 1 tail, and that's the job of the binomial coefficient, to let you know how many of those arrangements there are. You may see in a factorial expansion that you might need to know 0 factorial. By definition, 0 factorial is 1. And then finally, the calculator will calculate these binomial coefficients for you. So if you wanted to get 4C3, what has to happen is you put 4 on the home screen first, and then, like I said, you go to the math key, you go over that PRB menu, next to option 3, you'll see the combinatoric symbol, NCR, so you choose that one, it pops you back to your home screen, then you place a 3 there, you press enter, and your calculator will let you know that the answer is 4. Okay, I've turned to page 23. Let's go back to this coin flipping example and repeat part D and E from that example on page 21. What would be the probability of getting exactly 3 heads? Well, now using that binomial formula, which, let me remind you again, It was the probability of x equaling k, some certain exact number of successes. It's got the binomial coefficient nk multiplied by the success probability to the k and the failure probability 1 minus p to the n minus k. So if we follow that, in order to work on the probability of getting exactly 3 heads, I'll have 3 as the binomial coefficient, 0.5 the success probability, the probability of heads to the third power, and then the probability of tails, which in this case is also 0.5 to the 4 minus 3, and then here we go, binomial coefficient 4, 0.5 cubed, and 0.5 to the first gives us 0.25. That's the same answer we got on page 21 without all that work of writing out the sample space and the probability distribution table. And then now to get the probability of at least 2 heads, back to example E from page 21. Well, if we wanted to use the binomial formula here, that means 2, 3, or 4 heads. So we'd have to use that binomial formula 3 separate times and crunch out 3 separate probabilities to add together and get that same answer, 0.6875, that we got on page 21. Okay, so now some textbook exercises. If we look here, we have a bundle of 10 bare root rhubarb plants. Rhubarb is kind of a very tart, I guess, fruit. Kind of looks like a celery stalk, but it's more red than green. So the sales clerk tells you can expect 5% of the plants to die before producing the rhubarb. Assume that the bundle is a random sample of plants. Let y be the number of plants that die before producing rhubarb. Using the binomial probability formula, let's find the probability that y equals 1. Well, as we read through the context here, y is the number of plants that die. So in this case, success is in quotes here. Dying is success. So n is 10. P is 0.05. That comes out of the context of the question. So to figure out the probability that y equals 1, we get the binomial coefficient, 10c1, 0.05, the success probability to the first power, and then the failure probability, 0.95 to the 9th power. Multiply that out, and you have 0.3151. So we know that there's then about a 31.5% chance that one of the 10 plants purchased dies before producing rhubarb. Second example, would we be surprised if 3 or more of the plants die before producing rhubarb? Calculate an appropriate probability. So when it says calculate an appropriate probability, we wanted to figure out the probability then that y is greater than or equal to 3 in order to decide if we'd be surprised. In order to do that, since we're buying 10 plants, we wouldn't want to do this directly as 3, 4, 5, 6, 7, 8, 9, or 10. So let's figure it out based on complements. The complement of 3 or more is 2 or fewer. So we rewrite it, right? We do a rewrite. 1 minus the probability that y is less than or equal to 2. Well, less than or equal to 2 means 2, 1, or 0 plants die. So we do the binomial formula once again, 3 separate times. We calculate these 3 probabilities, subtract from 1, and we have 0.015. So something that's going to happen only about 1% of the time is surprising. We want to say that is surprising because the probability of observing this event of 3 or more plants dying is very small. And our general rule is going to be as if a probability comes out below 0.05, something that's got a less than 5% chance of happening, we are going to call that a surprising result. Okay, I flipped to page 24. Well, now on page 23, you probably thought, oh, those binomial probabilities, that's kind of annoying to calculate those. That combinatorics notation takes a long time to work out. Well, of course, there are some graphing calculator shortcuts now that we've saved to help you more efficiently answer those questions. So if you wanted to get the probability of a specific exact number of successes for that random variable you're counting, we have this command called binomial PDF. And this binomial PDF is found with second vars, press second then vars, go all the way down to letter A, and you will see this command, binomial PDF, P. And then if you wanted to get a binomial calculation for up to and including k successes, k or fewer successes, well then you see that there's a binomial CDF command next to letter B. So P for probability density function, C for cumulative density function. This one with the C is basically summing binomial probabilities for you up to and including the value k successes. Be careful with those inequalities. You're going to see the questions asking you about certain numbers of successes that are above, below, or between two numbers. So when you're asked for successes that are above, below, or between two numbers, I wrote out some notation here for you to talk about how you would use the binomial CDF and PDF commands correctly. But you will see me use these in some examples below. And then also, back on page 21, we calculated the mean and standard deviation for a binomial. And we did it the long way. We made you type in list 1 and list 2 and run the one_var_stats command. Well, it turns out that if you're a binomial random variable, you have a simple formula for a mean. Mu sub x equals n times p, and sigma x equals n times p times 1 minus p. Okay, so now finally, back to page 21, let's do that coin flip 4 times. X is the number of heads. If we determine mu x and sigma x, mu x is simply n times p. So for n times p, we're just going to have 4 times 0.5, which is 2. So of course that makes sense. We should expect 2 heads when we flip 4 times. And then for the standard deviation, n times p times 1 minus p. If we calculate that out, we do 4 times 0.5 times 0.5, and let's see what we get. Okay, so I got 1 for that. To find the probability of exactly 3 heads, the probability that x equals 3, that would be a binomial PDF command. And the inputs are 4 for n, 0.5 for p, and 3 for the number of successes. Type that in your calculator and let's see what we get. Okay, I got 0.25 for that. And then the last question, the probability of getting at least 2 heads. Well, at least 2 is 2 or more. And back on page 21, I did that out as the probability that x equals 2 or 3 or 4. Well, if I want to use the binomial PDF and CDF commands in the calculator, I have to rephrase this as 1 minus the complement. The complement of 2 or more is 1 or fewer. So I'm going to go 1 minus binomial CDF because I'm solving an inequality binomial calculation. And the parameters are 4, 0.5, and 1. So let's type that in our calculator and see what we get. Okay, I got 0.3125 for that. Subtracting from 1, I have 0.6875. Okay, so let me reiterate here. The only way to use this CDF command correctly is to have a binomial calculation where there's a probability up to and including a certain number of successes. So if you see x is greater than or equal to 2, the complement of 2 or more is 1 or fewer. So for that 1 or fewer, you go use the binomial CDF. In part D, the reason I have binomial PDF is because I have exactly 3 successes to figure out a probability for, while here I want the calculator to accumulate for me the probability that x equals 0 or 1, and then subtract that from 1 so that I can get the probability of 2 or more heads. Okay, flip to page 25. For the 3 examples that are here, I'm going to again demonstrate some binomial calculations for you. So first, as usual, it's important to read the problem, understand the context. So in our context here, we have 10% of students in a school who are left-handed. We are going to select 15 students, and we're going to let W be the number who are left-handed. Part A, find the probability that we have exactly 3 students left-handed, and then another, would you be surprised to find 4 or more left-handed students? So first, for the probability that X is exactly 3, that's a binomial PDF command. So binomial PDF, the inputs are N is 15, P is 0.10, and 3 for the number of successes we wish to calculate this binomial probability for, and calculator gives us 0.1285. Okay, what AP Stat would want to see for some work shown is next to the work and next to the context that we understand that X is a binomial distribution and that the parameters are N is 15 and P is 0.10. Just like we do in the normal calculations where we draw a bell curve and we write the mu and the sigma down, well, in a binomial, let's write down the N and the P. So then the second part B, find the probability that X is greater than or equal to 4. And to do that, again, because greater than or equal to is not something the calculator command will give me, the algorithm is specifically for binomial calculation up to and including a certain number of successes. So the complement of 4 or more is 3 or fewer. 1 minus the probability that X is less than or equal to 3. Again, binomial CDF command this time, and I got 0.055. All right? Well, now that 0.055 is really quite close to that 0.05 cutoff. So technically not surprising, but a little bit surprising because of how close it is to 0.05. Hence, I wrote this would be moderately surprising in a sample of 15 students to find 4 or more lefties. Next example. Lie detectors. So a federal report finds that lie detector tests given to truthful people have a probability of 0.2 of suggesting that the person's deceptive. A company asked 12 job applicants about thefts from previous employers using a lie detector to assess their truthfulness. Suppose all 12 answer truthfully. Let X be the number of people who the lie detector test says are being deceptive. So X is counting deceptives. So if X is counting deceptives and we are interviewing 12 people, we have an N equals 12 and a P equals 0.2. So remember, success in this problem, don't take it literally. In this case, success is finding a deceptive person. So if we calculate mu, we showed you that there was a binomial formula for that. Mu X equals N times P. So we take 12 times 0.2. So we would expect 2.4 on average 2.4 truthful persons will be identified by the lie detector as liars. And the standard deviation formula is sigma x equals the square root of n times p times 1 minus p. Crunch that out to 1.39. And now again, on average, the number of people who are found to be deceptive deviates from the mean of 2.4 by 1.39. Remember, standard deviation is always interpreted as an average deviation from the mean. Final example about lie detectors. Now we want to find the probability that y is greater than or equal to 10. So to do that, greater than or equal to 10, again, by complement rule, 10 or more's complement is 9 or fewer. So 1 minus binomial PDF, 12.8 and 9. So we have 0.5583. Okay, so in this case, notice that they changed the situation for us. They changed it to truth-telling. So if 2% are being deceptive, 20% are being deceptive, 80% are being truthful. So this calculation of 10 or more truthful people to be 0.5583, if you were to do it the other way, 2 or fewer liars, so 2 or fewer liars or 2 or fewer deceptives is binomial CDF 12.2 and 2. Notice we get the same answer. So the demonstration here is that be careful how you're defining the variable. If you're defining it as deceptive, n's 12 and p is 0.2. If you're defining it as truth-telling, n's 12 and p is 0.8. I'm on page 26. Last two examples for demonstrating some binomial calculations. Exercise 86. 1 in 6 wins. As a special promotion for a 20-ounce bottle of soda, a soft drink company prints a message inside the cap. Some caps say try again, while others say you're a winner. The advertisement is that 1 in 6 wins a prize. Suppose the company is telling the truth, and every 20-ounce bottle of soda it fills has a 1 in 6 chance of being a winner. 7 friends go buy the 20-ounce bottle of soda at a local convenience store. Let X be the number who win a prize. So in part A, we have to explain why X is binomial. So to answer part A, we're going to write out bins. All right, B for binomial. So condition number 1, 2 outcomes. Win or lose. Condition number 2, each bottle is independent. Condition number 3, fixed number of trials. And condition number 4, each cap has a 1 in 6 chance of winning, same probability of success. Therefore, X is binomial. X is binomial, and the parameters are 7 for n and 1/6 for p. Right, part B, let's find the mean standard deviation of X. So mu is n times p, 7 times 1/6. Let's calculate that. That's 1.17. Sigma is the square root of n times p times 1 minus p. So if there's a 1/6 chance of success, there's a 5/6 chance of failure. Let's calculate that. Okay, I got 0.986 for that. Interpreting that, I'm just going to speak here. So the mean, 1.7. On average, we expect 1.17 winners. And the standard deviation, we're going to deviate from that on average by 0.986. So now part C. The store clerk is surprised when 3 of those friends win a prize. Is this group of friends just lucky, or do we somehow have evidence that the 1 in 6 claim is inaccurate? Well, let's figure out this calculation. What is the chance of seeing 3 or more people win a prize on this 20-ounce bottle? So 3 or more, phrased in the terms of a complement, is 2 or fewer. So this is 1 minus the binomial CDF command. And the prompts there are going to be 7, 1 in 6, and for the value of X, we're typing a 2. Let's calculate that. Okay, I got 0.0958. And then, should the store clerk be surprised? This is not surprising. This is not surprising. Because the probability is greater than 5%. Okay, next example is about Scrabble. It may ring a bell. We did this problem in the simulation section of Chapter 5. So in a game of Scrabble, each player begins by drawing 7 tiles from the bag with 100 tiles. There are 42 vowels, 56 consonants, and 2 blanks. Kate chooses her 7 tiles and is surprised that all of them are vowels. Can we use a binomial distribution to approximate this probability? Justify your answer. Okay, so B for binomial, we either have a vowel or no vowel. I for independent, well, we are sampling without replacement, so the independence condition fails. But in this sampling without replacement, because the size of the population is more than 10 times the size of the sample, 100 tiles, is more than 10 times the 7 tiles, maybe we're willing to forgive that sampling without replacement idea. So if we wanted to calculate this probability and say yes, let's curiously calculate this probability. Okay, so the probability that all 7 are vowels is going to be found with the binomial PDF command. And let's see, N is 7. Success probability is 42 out of 100. And we're interested in exactly 7 successes as well. So what is the chance of this? Let's calculate it. Okay, so that is very low. It's 0.0023. Alrighty, so if we're willing to ignore the sampling without replacement because the 10% condition technically passes in the Scrabble tile example, we see that Kate has a very low probability of having a tray of all 7 vowels, and she should be quite surprised. Final example at the bottom. It is possible to make binomial probability histograms in your calculator. In this case, I will show you when we get back how to do this. But if you go into your calculator and you want to attempt this, here's what would have to happen. You can go create list 1. And if you're binomial 6 and 0.5 in list 1, you have to put the values of x, which are 0, 1, 2, 3, 4, 5, and 6. And then to create list 2, you can go at the top of the list, and at the top of the list, where it says L2, you highlight it in black. You can actually type the binomial calculator command on top of list 2, and here's what you'd be typing. So on top of that L2 box right there, you would type binomial PDF. You would type a 6 for N, a 0.5 for P, and you would tell it to get the X's out of list 1 and press enter. And then it would fill out list 2 with all those binomial probabilities for you. And then you can go into the stat plot, and in stat plot you can actually get this histogram to show up for this binomial distribution. And then notice I'm going to do binomial 6.2 and binomial 6.8. And the main idea here, the takeaway, is if you notice when the success probability is about 0.5 in 6 trials, you should expect the highest peak at 3, because on average, if you do something 6 times with a 50-50 chance of success, 3 successes should occur most often, but you can still get 4 or 2, 5 or 1 or 0 or 6 successes less often. And notice the nice symmetric distribution. If you have a binomial calculation where the success probability is low, well then the low number of successes are going to occur more often than the high number of successes, giving you a skewed right histogram. And then finally, we have a binomial with n is 6 and p is 0.8. So now the success chances is high. So if the success chance is high, you should expect the high values of x to have high probabilities and the low values of x to occur less often, giving you a skewed left shape on the histogram. So that's the moral of the story. Symmetric for binomial probabilities near 0.5, skewed right when binomial probabilities are low, and skewed left when binomial probabilities are high. Okay, I'm on page 27. Last topic in section 6.3 is to talk about a different type of count, and this count has a geometric distribution. Notice though, I'm sorry, I have a little scratch through right here. There is one small topic in the chapter called the normal approximation to the binomial. I'm going to omit that. Okay, so for geometric distributions. In the binomial setting, it's important to remember that when we were counting something, we were counting the number of successes in a fixed number of independent trials with the same probability of success. Consider these different situations instead, though, where x is a count of the number of trials needed to obtain the first success. So often in a chance process, we would like to watch that process until a first success occurs. Example, flip a coin until you get a head, roll a die until you get a 4, draw a card with replacement until you get a heart, have a baby until you have a boy. In each of these cases, x has a geometric distribution, and the following conditions are satisfied. We still have one of two categories, success or failure, independent observations, same probability of success, but now we're counting the number of trials required to obtain the first success. So in this case, x now follows a geometric probability distribution, and to find the probability of waiting until the nth trial to obtain a success is a very simple calculation, actually. If you notice what we're going to do here, all we do is assume then that the first n-1 trials resulted in failure, and finally the nth trial resulted in success. And now again, n is not fixed, so the values of x could start at 1, 2, 3, and they go on forever. Notice x can't be 0. In a binomial distribution, x can be 0, because in a fixed number of trials you can have 0 successes. But if you're counting trials until you get success, the value of x starts at 1. On average then, how many trials should you wait to get a first success? You'd wait 1 over p for that to happen, and the standard deviation, square root of 1 minus p over p squared. So guys, these formulas are not in the AP Stat formula booklet. AP Stat assumes that these geometric probabilities can be calculated very simply without having a formula in front of your eyes. The mean also is a pretty simple thing. The idea is if something happens 1 in 3 times, 1 divided by 1/3 would be 3. On average, I'd wait 3 trials to get my first success. AP Stat will never ask you for this standard deviation of a geometric distribution. However, my MAO people, mu alpha theta people, you might have to have this memorized, okay? I flipped to page 28. In order to do geometric calculations in the calculator, if you recognize some context as describing a geometric distribution, you have some graphing calculator shortcuts for this as well. Again, under the second VARS command, if you type second VARS and scroll down, you will see next to letter E, the geometric PDF command, and next to letter F, the geometric CDF command. Same notes about being careful with inequalities. If you have to get a geometric count above, below, or between two numbers, you have to use that CDF command correctly in each of these scenarios. The examples below hopefully will demonstrate some of that. So first example here is, can we identify something as geometric or not? In order to do so, let's check out the context. First, shuffle a deck of playing cards. Turn the cards over one at a time until you get an ace. Well, we have to say not geometric because turning cards over one at a time is without replacement and it makes the observations dependent. Second scenario, Lawrence is learning how to shoot a bow and arrow. On any shot, he's got a 10% chance of hitting the bullseye. Lawrence's instructor makes him keep shooting until he gets a bullseye. Well, now we are geometric. We have success and failure, either hit the bullseye or not. We have same probability of success, 10% on every shot. Let's be willing to assume that the shots are independent. Okay? And then finally, since we're waiting until we observe success, we have a geometric random variable in the case of shooting at a bullseye. Okay, so last two examples on page 29. Back to the 1 in 6 wins. Alan decides to use a different strategy for the 1 in 6 wins game. So he's going to keep buying a 20-ounce bottle of soda until he gets a winner. Find the probability he buys exactly 5 bottles. So now X, the number of bottles until finding a winner, it is geometric. P equaling 1/6. So the probability that X equals 5 means Alan fails 4 times and then wins. So I can simply take 5/6 to the 4th power times a 6th. Or if I feel like using the geometric PDF shortcut in the calculator, I can go grab geometric PDF under second varies, type in 1/6 for P and 5 for X, and we get 0.0804. Part B, what's the chance he buys no more than 8 bottles? Well, for that inequality, no more than 8 means X is less than or equal to 8. No need to manipulate that because that's exactly what the CDF command will give us. Geometric CDF, typing in 1/6 for P and 8 for X, gives us 76.74% chance. And finally, a part I added. Let's do a between 5 and 8 inclusive. So for between 5 and 8 inclusive, look how clever you have to be. On a number line, remember X could be anywhere from 1 up to whatever it takes to get a first success. I'm interested in the interval 5 to 8. So I'm going to ask my calculator to figure out the cumulative sum up to 8. But because I only needed 5 through 8, I have to subtract off the cumulative sum up to 4. So in this calculator command, then, we need the probability that X is less than or equal to 8 minus the probability that X is less than or equal to 4. So to finish that, you're going to run this geometric CDF command twice. So I'm just going to write GCDF, and I'm going to type in a 1/6 and an 8, and then I'm going to minus off a GCDF with a 1/6 and a 4. So let's go do that in the calculator. Okay, so I got 0.7674 minus 0.5177 for a final probability of 0.2497. And final example here. So using Benford's law, the probability that the first digit of the amount of some randomly chosen invoice, being an 8 or a 9, is 0.097. We're going to examine randomly selected invoices from a vendor until we find one whose amount begins with 8 or 9. How many invoices do you expect to examine until you find one that begins with an 8 or 9? So for part A, if X is the number we examine until finding 8 or 9, that's going to be geometric, and the success probability, I guess, would be 2 in 10. So 8 or 9, remember there are 10 different digits, so to find an 8 or a 9, that would have a 2/10 chance. So to figure out the mean, mu x, it's simply 1 over 2/10. So we would expect to examine 5 invoices until we find one that has a beginning number of 8 or 9. And part B, in fact, you don't get an amount starting with 8 or 9 until the 40th invoice. Do you suspect that the invoice amounts are not genuine? Compute an appropriate probability. So the appropriate probability is not X equals 40. It's at least 40. What's the chance of finding 40 or more invoices examined until we find one beginning with an 8 or 9? So the appropriate probability to answer the "Are you surprised?" question is always talking about a result that's as or more extreme than the one I got. So if I waited 40, that sounds like a long wait. So as or more extreme than the one I got is X greater than or equal to 40. So we are going to rewrite that using the complement rule as 1 minus the probability that X is less than or equal to 39. That's 1 minus the GCDF command. And the parameters are 2/10 for P and 39 for X. Let's crunch that out. So I got 0.000166 for this. A very, very slow chance, small chance. So what that means is it's a surprising result. So this company whose invoices I'm examining, since I got such a surprising result, I'm now starting to think that these invoice amounts are not genuine. This low probability has clued me into something suspicious. All right, that's the end. Well, as usual, I'm sure my explanations were quite long-winded. Hope this helped. I hope you're either reading the note packet, watching my video, or Mathman Bill G's video to learn this section 6.3 at some time over your winter break. Remember, the homework for this section is due after break, plus a problem set that you were given is due after break. I'm not going to be spending too much classroom time teaching this, hoping that you could take it upon yourself to learn one section, one very important section, because binomial calculations are definitely on the AP exam. And the geometric calculations, not so much, because as you saw, you could really solve one of these geometric problems without really needing these fancier calculations.